Large language models do not possess cognitive knowledge, and they do not reason in the way humans do. Viewing these systems as synthetic brains leads to a misunderstanding of their underlying engineering. These are complex vector engines. They store and approximate information as mathematical manifolds plotted within high-dimensional spaces. Analyzing these models requires focusing on the linear algebra, specifically how data points are distributed across these geometric axes. We will trace the mathematical pipeline of a single prompt, following the data as it transforms from a text string into a specific output token. Managing an LLM's output effectively depends on navigating the geometric reality of this high-dimensional architecture. Take a standard prompt: "What is the capital of Vietnam?" The model cannot process this as text. The input is broken down into discrete pieces, based on a vocabulary of roughly 40 to 50,000 known tokens. Each token is then translated into an embedding, a dense numerical array. This specific embedding operates in a space of 12,000 dimensions. This high-dimensional coordinate is where the token's mathematical meaning resides. These embeddings form the sequence of data structures that pass into the neural network. To process them, the network applies nonlinear activation functions, such as ReLU or GeLU. Functions like ReLU, which takes the maximum of 0 and the input value, allow the network to model complex relationships between tokens that a simple linear model would miss. The prompt is now a pure, high-dimensional algebraic object, ready for dynamic computation. Traditional neural networks rely on fixed, static weights to combine information. The transformer architecture uses an attention layer to compute weights dynamically in real time by using scalar dot products. This mechanism generates 3 distinct vectors for the token being processed: queries, keys, and values. The current token generates a query, mathematically compared against the keys of all previous tokens to measure similarity. In money in the bank vector yields a high scalar product with money, but in riverbank, it routes toward river. This occurs at a massive scale, with modern models running 96 simultaneous attention heads. Each head processes 128 dimensions to maintain the total 12,288 dimension structure of the model. These computed similarity weights are then used to linearly combine the value data and pass it to the next layer. Because text generation is autoregressive, the system must retain keys and values for all previous tokens in memory. This KV cache is a significant hardware constraint. This attention mechanism functions exactly as a dynamic, real-time matrix multiplication, mathematically rewiring data based on surrounding coordinates. Following the attention mechanism, the data moves to the feed-forward network, or FFN. While an attention layer requires roughly 300,000 storage units, the FFN requires over 1.2 million. This table highlights the scaling dilemma. Increasing the size of a monolithic model increases capability, but it significantly slows inference speed and raises compute costs. Modern architectures bypass this by shifting from dense networks to sparse networks. The engineering solution to the FFN bottleneck is the mixture of experts architecture. A router calculates probabilities to determine the specific path a token should take through the layer. Instead of using the entire network, the router sends the token only to a few specialized subnetworks. Large-scale models can possess multi-trillion parameters spread across 256 expert slots. Out of those 256 experts, only 8 might be active for any given token during inference. Hypersparse selection decouples the model's total capacity from its inference cost, allowing for broader scaling on existing hardware. These internal blocks are structured into different macro architectures depending on the system's purpose. The decoder-only architecture is the standard for models like GPT. It is autoregressive, meaning it generates one output token which is immediately looped back into the context window for the next cycle. We can contrast this with encoder-only architectures. Encoders ingest the entire context block in parallel to produce a batch of output tokens at once, making them useful for classification rather than generation. Hybrid encoder-decoder systems use a left context block to feed computed attention coefficients into a distinct right context block. While the vector algebra is consistent across these types, the pipeline arrangement determines if the model acts as a generator or an analyzer. Our original token now exits the 96th and final transformer block. It remains a high-dimensional vector in a 12,000-dimensional space. This vector is then mapped back onto the 50,000 dimension vocabulary space to produce raw scores called logits. A softmax layer normalizes these scores into a probability distribution. The token with the highest probability, in this case Hanoi, is selected as the output text. Because the output is derived from mathematical probabilities on a manifold rather than a database query, it produces probable information, not guaranteed facts. While LLMs are highly effective for pattern reasoning and data transformation, their foundational reliance on probability makes human verification a requirement.